going to be looking at half-life and the key constants. But before we look at these particular concepts, I want us to remember that these concepts were coming from the topic radioactivity, and we need to have a background of that topic before we look at this. Okay, what is radioactivity? From our basic knowledge of physics and radioactivity, we say radioactivity is the process whereby the atom of a naturally existing element emits radiation or particle as a result of a spontaneous disintegration of the atomic nucleus of that element. Okay, that is radioactivity. The disintegration that happens in radioactivity emits particles, such as particles emitted during radioactivity, particles emitted during radioactivity are, we have alpha particle, and the alpha particle emitted is helium nucleus. Okay, we have beta particle, which is electron, and then we have a gamma ray. This is not necessarily a particle, it is an electromagnetic radiation. Gamma ray, it has no element representation. Okay, these are the basic particles emitted by during radioactivity, either any of these or a combination of them. So this is what we have during radioactivity. The alpha particle was observed to have an effect, or that the electrical field or magnetic field has an effect on this particle. When an alpha particle passes through an electrical field, it slightly deflects. That is, if you have a negative charge and a positive charge, an alpha particle, when it wants to pass through this electrical field, it has a slight deflection to the negative, because an alpha particle is a positively charged element. Okay, an alpha particle is a positively charged particle, so it has an attraction to the negative polarity of the electric field, and so it is attracted to it slightly. Then a beta particle is negative, and because of that, it has a strong deflection to the positive charge. That is, beta particle, which is negative, has a strong deflection to the positive because it has to attract to the opposite polarity. While the gamma ray, which has no charge, has no deflection, it moves straight. Also, an alpha particle has a strong ionization strength. It has a strong ionization strength or ability. A beta particle has a weak ionization strength, while a gamma ray has little or no ionization strength. Okay, you can see that this is where we are going to stop for this one. I will not proceed to mention other properties of these particles. Okay, because our interest today is half-life and decay constant. I'm just giving us an introduction of how these things came. Okay, so other particles that a radioactive element can emit are, we have the proton, which is P11. We have the neutron, which is N10. Okay, then in radioactivity we can have artificial. There are two types of radiation that can happen. It can be artificial radioactivity, and we have natural radioactivity. You see, from the name natural and artificial, we know that this natural is the one that occurs spontaneously, the one that occurs without any external effect. Radioactivity that occurs spontaneously, emitting alpha particle, beta particle, gamma ray with the release of energy. While in artificial radioactivity, it happens when there is a bombardment, when a non-radioactive element is bombarded with a radioactive particle. so that it will make this non-radioactive element to become radioactive. So that is artificial radioactivity. While natural radioactivity occurs spontaneously, it occurs without any external influence or effect. Okay, that is not our interest. Let us look at what we have come to look at, which is half-life and decay constant. What is half-life? Half-life, T half, that is what I used to represent half-life, is the time taken for half of the half-life of a radioactive element, is the time taken for half of the atom present in that radioactive element to disintegrate or decay. Is the time taken for half of the atom present in a radioactive element to disintegrate. That is half-life. If a radioactive element has a number of atoms n present at a given time, and the rate of decay, the rate at which this radioactive element will decay, is said to be proportional to the number of atoms present in that element at that time. This is a relationship, and we know that in mathematics, if we remove the proportionality sign and introduce an equality sign, we have a constant. Here we call it a decay constant. Okay, and then if we divide this by n, this will cancel this, and decay constant will become minus delta n over delta t divided by n. That is decay constant. So we can now define decay constant as the rate of decay, of a radioactive element per unit number of atoms present in that element at that time that decay happened. The rate of decay of a radioactive element per unit number of atoms present in that radioactive element at that time the decay happened. We're having minus here because decay is a reduction in size. So it is a decrease, not an increase. If it was an increase, this would have been positive. But because the rate of decay is a decrease in size, that's why the minus is here. So decay constant is the rate of decay of a radioactive element per unit number of atoms present in that element at that time. So if we still work with this, if we cross multiply this relationship, we're going to have that minus delta n is equal to lambda n change in t. Okay, and then we can move this minus to this side or multiply both sides by negative, so that we have that change in n is equal to minus lambda n change in t. Okay, then mathematically I want to get us a formula that we use to determine the number of atoms that is going to remain on a certain element after a certain number of time. Okay, if we integrate this and also integrate this, we are going to have n here. If we integrate this, if you know the integration, we will have n here. And then if we integrate this one, we will have n naught exponent minus lambda t. And this formula is what we are going to use to determine the number of atoms present in an element after a decay. So this n represents the number of atoms present or remaining after disintegration or after a certain number of time that a radioactive elements have actually decayed. While n naught is the number of atoms present in that element before decay. Lambda is the decay constant, while t is the time for the decay. Okay, remember that the time for the decay is not always half-life. Remember that the time for the decay is not always half-life. Half-life, I represent it with T half. And if the time for the decay is not half-life, it is just T. So if the half-life, let's say that half of an atom of an element will decay in 5 years, it means that the half-life is 5 years. What if it doesn't mean that the element will not decay until after 5 years? No, it can still decay gradually before 5 years or even after 5 years. So after 3 years, and the element, we want to determine the number of elements, or atom of that element that is remaining after 3 years, while the half-life is 5 years. The time 3 years is this, not half-life, because the half-life is 5 years and it has not gotten to the half-life. So we can have half-life and also time of decay, which may or may not be a half-life. So if this is the formula to determine the number of atoms remaining after a certain number of time for a radioactive element, we can as well know that for half-life, we say that the number of atoms remaining after half-life is going to be the time, the half-life is the time taken for half of an atom of an element to disintegrate. So the number of atoms that will remain after half-life should probably be half of the original number of atoms before decay. So after half-life, half has decayed, and this is the number that will remain, half of the original number. Remember I said N naught is the original number of atoms present in a radioactive element, while N is the number of atoms present after decay. So if N is here is now the number of atoms present after half-life, then half N naught will be equal to N. Okay, and we can comfortably replace N with half N naught in this other equation, so that we have half N naught equal to N naught exponent minus lambda. This time T is half-life because we have represented the number of atoms present with half of the original number of atoms. Therefore, the time for this to happen, it should be half-life. And you can see that N naught here will cancel N naught, and we have half equal to exponent minus lambda T. And of course, this half can be written as 2 raised to power minus 1 equal to exponent minus lambda T half. Okay, if we take the natural logarithm of both sides, that is ln of both sides, of course in logarithm, this thing, the law of logarithm, this minus power can move behind. We have minus 1 ln 2 equals this one can also move behind. We have minus lambda half-life ln E. Okay, and we know that this ln E is the same thing as log to base E. Ln is log to base E, that is log E base E, which is 1. So, and then we have minus 1. If you punch your calculator to get ln 2, you will have 0.693 as the natural logarithm of 2. And then it is equal to minus lambda half-life, because this ln E will be equal to 1. Okay, the minus here will cancel the minus here, so that if we make decay constant is, or let's say we make the half-life the subject of the formula, we'll have 0.693 over decay constant. So this relationship between half-life and decay constant, the half-life is equal to 0.693 over decay constant. We use this formula to determine that. And remember, originally I have given you that the number of atoms that will remain in a radioactive element after disintegration equal to the original number of that atom before disintegration multiplied by the exponent minus lambda T. Okay, if we know this, then if we make lambda the subject of the formula here, we have that lambda is equal to 0.693 over half-life. And if we should use this to replace lambda in this other equation, we have N equals N naught exponent minus, instead of lambda we have 0.693 over half-life times T. So the whole of this is representing lambda here. Okay, and then we can simplify that N equals N naught exponent minus 0.693 times T over T half. Okay, and if you could punch this in your calculator, exponent minus 0.693, you are going to be shocked to get 0.5. That means I can actually represent this with half. The whole of this exponent minus 0.693 with half. That means it's going to be half raised to power T over T half. Okay, this is also a formula we can use to determine the number of atoms remaining after disintegration. We can decide to use this if you have your lambda, the decay constant, or use this if you have your half-life. So either this or this, while this is the relationship between the half-life and the decay constant. Okay, so you can actually punch your calculator to confirm that exponent minus 0.693 is 0.5, where N is the number of atoms remaining after decay, N naught is the number of atoms present before decay, while T up here is the time of decay, and T half is the half-life. Okay, this is a relationship we are going to use to determine whatever we are going to solve under half-life and decay constant. Let us look at few examples to be able to see whether we can solve them. Okay, this question said a sample of radioactive material has a half-life of 35 days. As usual, we list our parameters. Half-life of 35 days is a solution. So we say that T half is 35 days. Okay. Calculate the fraction of the original quantity that will remain after 105 days. That is, the time for decay is 105 days, while the half-life is 35 days. First of all, let us use this formula. N equals N naught 1 over 2 raised to power T over half-life. We are looking for a fraction of the original quantity that will remain after 105 days. Okay, this is the quantity that will remain after a certain number of days, and this is the original quantity, N naught. Okay, and this is 1 over 2, while T is 105 divided by half-life, which is 35. If we do that, we have that N equals N naught 1 over 2 raised to power 105 divided by 35, you have 3. And we know that N equals N naught 1 raised to power 3 is 1 and 2 raised to power 3 is 8. So a fraction of the original quantity that will remain is 1 over 8 of the original quantity. That is the answer to this question. A fraction of the original quantity of atom that will remain after disintegration or after 105 days is 1 over 8 of the original quantity. You can use this. Let us even decide to use the other formulas that I gave you to compare the answers. You can as well see that N equals N naught exponent minus lambda T. If you are using this one, that means because from this we don't have our lambda, and we know that we can get our lambda using the formula 0.693 all over half-life. Okay, you remember that I gave you. So it means that decay constant lambda is equal to 0.693 divided by half-life, giving us 35. Okay, so if we put that into this formula, we are going to have that N equals N naught exponent, instead of minus lambda, we'll now have minus 0.693 divided by 35, then times T, which is 105. Yes, so that this is going to give us N equals N naught exponent minus 0.693. 35 we divide 105 to give us 3, then times 3. And if you punch exponent raised to power minus 0.693 times 3, you are going to have 1 over 8. So we have 1 over 8 also, N naught. So whichever one you want to use, you can still do that. Alternatively, we can even solve it without a formula. So let us see how we can do that. Now, if we understand this, that the half-life of a radioactive element is 35 days, that means that if after 35 days, the number that will remain will be half of N naught, because half has decayed. So this is the number remaining. After another 35 days, which is 35 plus 35 will give us 80 days, so 70 days, sorry. 35 plus 35 will give us 70 days. So after 70 days, the number that will remain will be half of this half, because half of this half will also decay again, and we'll have half N naught, and that will give us 1 over 4 N naught. Then after another 35 days, which is after 105 days, Remember, this is what is remaining. 1/4 is remaining after 70 days. So after another half life, which is 105, if you add 35 to 70, that will be half of 1/4 n0 will remain, and that will give us 1/8 n0. You see, we are getting the same thing. So it depends on which method you can use, but this method is only applicable if the number of the time for the decay is a multiple of the half-life. If it is a multiple of the half-life, 2 times the half-life, 3 times, 4 times, 5 times the half-life. But if the time for the decay is not a multiple of half-life, like if this is 100 days, you know that 35, multiple of 35 cannot give you 100, then we can't use this last method. Is it that we use the first or the second one, where we can substitute directly the half-life and the time for decay. So you should take note of that.